Huge progress has been made in understanding neutrino-driven explosions, and very likely most ordinary supernovae come from moderately or non-rotating massive stars. However, we detect a number of supernova events with a large or very large implied kinetic energy, as can be seen from this so-called hypernova branch in Nomoto's et al. 2013 plot. These events are most likely linked to stellar cores with large magnetorotational energies. Furthermore, explosions of stars between, say, 13 and 25 solar masses cluster at typical supernova energies of the order of 10 to 51 Earths, while explosions of stars, of massive stars between 25 and, say, 40 solar masses may be falling in the faint supernova branch or in the hypernova branch. On this right sketch, you see a sketch connecting explosion types with the kind of compact remnants that we may expect from them. While neutron stars are the typical outcome of ordinary supernova explosions, magnetars are proposed to explain the observed light curves of superluminous supernovae and perhaps of some hypernovae. Finally, rotating black holes are expected to be compact remnants behind the production of long GRBs, the latter probably having the largest magnetorotational energies in stellar progenitors. It is anyway clear that we need to understand better the transit to magnetorotational explosions as well as what elements in collapse and in the explosion phase induce changes in what I may call the genetic heritage imprinted by the stellar progenitor on the compact remnant. One of such elements is the process of magnetic field amplification that may significantly slow down the protoneutron star producing magnetars. Another interesting aspect to look at is the question of whether there is a mass gap between neutron stars and black holes, or whether there is a smooth transition. And finally, you should bear in mind that there might be a difficult to quantify fraction of events which do not yield successful supernova explosions, and therefore they are difficult to notice observationally. From an observational point of view, it is clear that massive stars tend to rotate rapidly. This figure from Huang and Guies, 2006, shows the probability distribution, the probability density per kilometer squared and second of rotational speeds of nearly 500 B-type galactic stars. And there you can see that the peak of the probability distribution function is at around 200 kilometers per second for the rotational speed at the equator, and that there is a non-negligible fraction of events rotating faster than 300 kilometers per second. From a theoretical point of view, it is clear that we know that rotation drives internal circulation and currents of various types, as well as turbulent motions whose origin is related to the stellar differential rotation. All these effects can contribute to internal transport of angular momentum and of chemical species. To what extent does incorporating rotation affect the type of explosion that a massive star can produce? Some answers can be found in this paper by Groth and Workers, 2013, where we can see that rotation affects the percentage of models that end their lives exploding as hydrodynamic supernovae of the different times we know of. For example, the presence of rotation increases the number of possible 1C supernova parents by almost a factor of 3, going from 5% to nearly 14%, because the available progenitor stars producing these models goes from stars above 50 solar masses if they are non-rotating progenitors to only 30 solar masses if they consider rotating models. Although rotation and magnetic fields require a genuinely 3D treatment, the practical need of being able to evolve the stellar models for billions of years requires that models or recipes be implemented in one-dimensional stellar evolution simulations. Typically, the transport problem is addressed by using diffusion coefficients, sometimes some approximated advection treatment, which contain adjustable coefficients. The calibration of these coefficients can be done using direct numerical simulations in 3D or using observational data. The stellar evolutionary calculations of most groups working in the field do not directly include magnetic fields as a basic variable. The magnetic field only appears as a mean to transport angular momentum, which happens due to the action of the so-called Tyler-Sprout instability. The Tyler-Sprout instability yields a dynamo cycle, which is as follows. You have a seed initial colloidal field, and this seed initial colloidal field, it's stretched by differential rotation, producing a toroidal magnetic field. Once you have a toroidal magnetic field, it can become unstable to the Taylor instability, producing colloidal magnetic field and then closing this cycle. As a result of the magnetic torques produced by the generated field, the profile of a specific angular momentum is modified. Precisely these panels on the left, you can see in the black lines, forget about all other lines, the distribution of a specific angular momentum as a function of mass on the horizontal axis. The action of the Tyler-Sprout instability only acts when there are certain conditions met locally in shells of the star, and requires in particular that the mass shell be radiative. That is to say that in convective layers of the star, this is not at work. The green hatch areas in these plots represent layers where the Taylor-Sprout instability was at work at the moment of computing this model. Elsewhere, in these white regions, there is no magnetic field according to state-of-the-art stellar evolution calculations. Since the growth rate of the Tyler-Sprout instability is so large, the field grows basically instantaneously relative to time scales of stellar evolution up to its saturation values, which are estimated here. And I say estimated because they depend on the magnetic diffusivity, which is somehow a parameter in this model. So it's computed through various approximations. Hence, the magnetic topology of the field and its strength displays a large variability, and because this is not the result of a self-consistent MHD calculation. And in addition, I want to stress that the relation between the toroidal and the poloidal magnetic field components, it depends upon the estimated effective magnetic viscosity. The properties of a collapse core, a recently collapsed core producing a proto-neutron star at formation depend clearly on the precise stellar structure at collapse. This structure may be very different, as you can see here, the plots of the density, the entropy per baryon, and the so-called compactness parameter, which I will come back later on. And you see here a range of possible masses in the range of massive stars that we will consider in this talk, where there is a wild or rather broad variability in those profiles. One of the most important factors shaping what happens to fast rotating stars is the possibility of enhanced mixing as a result of this fast rotation. This enhanced mixing can yield what we call chemically homogeneous evolution, in which the stellar core may still retain a large amount of angular momentum at the presupernova link, that is just at the brink of collapse. Here you have also another important ingredient in the outcome of the compact remnant and of the explosion, namely the fact that in the previous seconds or minutes prior to the pre-supernova link, convection in the silicon oxygen shell can create non-radial perturbations of the medium in which a supernova shock shall propagate later on. These perturbations help breaking the spherical symmetry of the medium and hence facilitate the supernova explosion as it has been seen by various groups in this papers and others. So effectively, they reduce the critical neutrino luminosity needed to accomplish a successful supernova explosion. I will try to show in this talk that a relatively small variance in the progenitor's properties may completely change the fate of the compact remnant. So the PNS that forms right after bounds may further collapse to form either a black hole or continue as a protoneutron star for a long while until it forms a neutron star. For the specific progenitors, stellar progenitors in this talk, this means that one may form central engines that can be a proto-magnetar. So if the compact remnant persists as a neutron star with a lot of magnetic field, or a collapsar if a black hole forms and it is girded by a thick accretion disk. Our long-term goals are inferring the properties of the stellar progenitors for those of the compact remnants left after core collapse, employing a multidimensional neutrino relativistic MHD simulation. The focus here is on a relatively fast rotating models with different degrees of magnetic energy and low metallicity, which are likely progenitors of long gamma reversed and superluminous supernovae. In particular, we are concerned about the explosion feedback on the compact remnant properties, the dependence of the stellar conditions, or what I have called before the genetic heritage, on the type of central engine form, whether a proto-magnetar or a collapsar forms, the prospects for supernova explosions in addition to black hole formation, because I remind you that if there is no supernova explosion, it is a very good assumption saying that the massive star will form a black hole. But the opposite is not necessarily true. You may form a black hole and also a supernova explosion at a time. There is an aspect I won't touch upon specifically in this talk is the formation of jets and their properties in the context of these fast rotating and magnetized models. And finally, I will say a few words about the multi-messenger signature expected in these scenarios, focusing on gravitational waves and nucleosynthesis. Our work is framed within a broader context than the one specifically touching upon superluminous supernovae and long GRBs, namely progenitors in general of supernova explosions. These fields, these models, these papers, previous papers, this is not an exhaustive list, there are probably, certainly many more, have studied the magnetorotational collapse, especially making emphasis on the rotational part, and not so much on the magnetic field. So recently, a number of practitioners in the field have jumped upon the action of magnetic fields. And the aspects that these works have touched are very broad and beyond the scopes of the things that I want to tell you right now. Magnetorotational core collapse and assessing the final fate of collapsing cores, as well as their observational transients, it's a multi-physics, multi-scale complex problem that can only be comprehensively dealt with numerical simulations. We start by mapping one-dimensional stellar evolution models into 2D or 3-dimensional grids, and typically the stars, which we are considering are rather compact, they have radii of a few 10 to the 10 centimeters, and we map only the first, say, 10 to the 10 centimeters into our computational grid. We take a neutrino relativistic MHD Eulerian code, which equips a two-moment neutrino transport, relatively sophisticated, not perhaps as much as shown by Tony Metzacapa yesterday. It includes also a tabulated equation of state, and the domain is discretized in a number of cells in 2 dimensions or 3 dimensions, as you can see here. Admittedly, the 3-dimensional models have a relatively low resolution, but this is because we want to run a sufficient number of models for sufficient time to quantify a number of effects. Regarding the magnetic field and the rotation, we take them either from, as they come, from the stellar evolution, and then you see that in a stellar evolution, the magnetic structure, it's a set of alternated layers with magnetic field and without magnetic field, and also the rotation, but this structure is certainly non-physical. You cannot expect to have layers devoid of magnetic fields in the neutrons in the stellar evolution. And then what we might do is to replace this original magnetic field by some likely distribution, bipolar or multipolar, to perform our models. Regarding rotation, we take normally a stellar rotation, and in some cases we consider a homogeneous multiplying or dividing factor homogeneously acting all over the star. We have organized the models in order to serve two goals. The first goal is to consider the impact of the variation of stellar evolution parameters of fast rotating cores, which at 0h mean sequence have 35 solar masses, on the compact remnants and their explosion times. Forget for a moment this control case. Let's focus on these two. These are two cores coming from the work of Buzdi and Heger in 2006, which have in common that they incorporate the Tyler-Sprout dynamos in stellar evolution to account for the transport of angular momentum and rotation. And both cases are low metallicity stars, 10% solar. They have relatively heavy iron cores in excess of 2 solar masses and are fast rotating. The difference between the two is that model OV has undergone a larger mass loss throughout its evolution because the parametrized mass loss rate is larger in that model than in the other one. The second goal is to assess with 2D and 3D simulations the kind of compact remnants and explosion types of a broader range of progenitor masses, most of which undergo what we call chemically homogeneous evolution. These models correspond to the so-called B series of Aguilera and Dena and co-workers, 2018. And in these models, fast rotation increases the diffusion of elements and makes that until roughly the end of helium burning, there is not really a core envelope structure in the star, but rather a homogeneous star. Only after that, one sees a core developing, but this core retains a relatively high angular momentum. And these progenitors have the property that have lost the hydrogen envelope, and they only preserve a tiny amount of helium, less than 6% of a solar mass. And thus, since they don't have hydrogen and merely helium, they are excellent candidates to produce type 1c supernovae. And therefore, they are excellent potential candidates to produce superluminous supernovae and gamma ray bursts. These models have low metallicity and they are also fast rotating, include Tyler-Sprout dynamos and mass loss. The models, this is just, I don't want you to go over all the details of the tables, but the table on the left corresponds to 2D models. The lower table is a subset of these 2D models, which has been run in 3D. And the right table corresponds mostly to models which have undergone chemically homogeneous evolution. First, let me guide you through the last column, which is this Xi 2.5 parameter. This is the so-called compactness parameter. The compactness is defined for a given mass shell of mass m as the ratio of this mass to a solar mass divided by the size, the radial size of this mass shell normalized to 1,000 kilometers at the time of bounce. This matrix, which is a dimension-less quantity, was found by O'Connor and Ott to be quite important, deciding whether a black hole and therefore not a supernova explosion happens, or whether a neutron star results from the collapse if the compactness is smaller or larger than a threshold that they put on a value 0.45. Our models are slightly above, the models coming from Buzdi and Heger are slightly above this threshold, and therefore, in principle, explosions should be very difficult to achieve, and you expect that in all cases, one would produce a black hole instead of a neutron star. Right, the compactness ratio has a much broader range of variability for the chemically homogeneous evolution models. Now, the second thing that I want to look at is just the fact that these models are magnetized and they are predominant. The dominant magnetic field component is the toroidal one. with typical strengths of the order of 10 to the 12 Gauss in the core in these models, while for the other models is somewhat less, of the order of a few times 10 to the 9 Gauss. The poloidal magnetic field is of the order of 50 times smaller, right? So it's a subdominant component in all these models. And as I mentioned before, it's just obtained as a saturation value, which basically derives from the value of the toroidal magnetic field component. So what we have done is to allow for small variations of factor 2, 3, 4, or a bit larger, and see of the poloidal field component in the stellar evolution model to see what's the impact on the post-bounce evolution of these models. In other cases, we have touched upon the rotational profile or the rotational profile and the magnetic field structure to understand the systematics. In the case of progenitors of chemically homogeneous evolution, we just simply scan across the mass range, where the model names are just A for Aguilera and then at 2018, and then two numbers stating the mass at 0H main sequence from 0 to 39 solar masses. In 3D, we give nicknames to our models: W for the weakest magnetic field, O for the original stellar evolution model, P for this case where we multiply by 3, only by 3, the poloidal magnetic field, which is still subdominant with respect to the toroidal one. And S is the strongest magnetized model, which also bears a dipolar structure. So the reference model produces a supernova mediated by contributions of neutrinos, magnetic fields, and rotation. And the explosion has a considerable magnetic contribution. It's very well collimated, as you can see here in 2D, 3 different snapshots. The ruler represents 100 kilometers in the mid panel, 1,000 kilometers in this right panel. And you can see that this high collimation is preserved also in 3D. This is just the topology of the magnetic field in 3D of the very same model at a similar time as this right panel over here. The PNS, which is displayed here with as well, what we display in this map, in this color map, is just the electron fraction, and the PNS is here at the center. What it happens is that the mass of this PNS grows after bounce as a result of mass accretion. Even if the explosion starts to develop, this explosion, as you have seen, is predominantly bipolar, and therefore accretion can still go along the equatorial region. That accretion lets the mass grow, but lets that the mass of the PNS grows. But at the same time, there is mass scratched from the outer layers of the PNS, which goes into the ejecta outflow. And then there is a balance between these two processes. The netto, in most cases, is displayed in this background plot, where the reference model is just highlighted with this green area over here, is that the mass grows. And it grows so much that eventually, after about 1.5 seconds after bounce, the reference model crosses over the limit that Luciano was mentioning above, before. This is the maximum mass a cold, non-rotating neutron star would have for the equation of state we are considering here, which is Latimer-Swesty with a compressibility modulus of 220 mega electron volts. But since these bodies, these PNSs, are highly differentially rotating and still very hot, they are centrifugally supported, and they can live for a long time or relatively long time with a mass above this limit. The particular case of the reference model in stellar evolution, it's that after about 3 seconds, this PNS may collapse to a black hole. And considering the distribution of a specific angular momentum in the outer layers of the star, which are being accreted or are falling onto the compact remnant with time, eventually these layers may form a centrifugally supported accretion disk. So we have the two basic elements, an accretion disk, a central black hole, to form a collapsar. So this reference model could yield a collapsar plus a supernova mediated to a large extent by magnetic fields. and to a lesser extent by neutrinos. We have, the gravitational wave signal from the bounce and the early post-bounce phase in rapidly rotating progenitors has been already quite extensively studied in a number of previous papers. I just listed here a few of them. We have computed some preliminary gravitational wave spectrogram, and in the bottom here, I show a zoom of the gravitational wave amplitude around the time of bounce. You see that the amplitude is not too large, neither they're not in the half a second or a bit more that trails this bounce phase. And this is because convection is very moderate in the post-bounce phase, probably because we have not included any perturbation, any random perturbation in density or velocity in the initial model, as could likely be the case, as I have explained before, if there is convection in the silicon oxygen burning layer. Another important thing is you can note in the gravitational wave amplitude is the memory effect triggered by the ejecta going into the bipolar, into the rotational axis, towards the rotational axis. And this, unfortunately, won't be easily detectable by the LIGO, Virgo, CAGRA detectors, current detectors, but maybe is within reach of the Einstein telescope or the Cosmic Explorer. What is more obvious here is that there is a very broad range of high spectral power, extending from a few hundred hertz to about 2 kilohertz, which looks like a broad F mode. And Pablo Cerdá should forgive me here because I have not made a proper identification of the mode, and this is disputed whether F or whatever other mode is. Actually, we cannot find any clear mode out of in these spectrograms so far, right? But in a way, this is consistent with results of Jardine, Powell, and Bernhard Müller, which have shown recently for magnetorotational supernova signals of axisymmetric models, where they see also this broad range of high spectral power, and as well as the memory effect that I was just mentioning before. We obtain a diversity of explosions, and we start first by considering the case of a fixed 35 solar masses initial mass, and variations, small variations of the rotational and or the magnetic field profile. One may see that most of our models end up exploding, although the explosion is achieved by different mechanisms. For instance, the model A here in 2D, which corresponds to these 3D models, here I'm representing the inverse beta parameter, that is the ratio of magnetic to thermal pressure. And here, this is the baryon the entropy per baryon. So this first model explodes as an ordinary supernova, neutrino-driven supernova, aided by hydrodynamic instabilities. But instead of forming a neutron star, it forms relatively quickly after bounce a black hole. We have other models, including the reference stellar evolution model, which is in panel C in 2D and here in 3D, where rapid rotation creates the conditions for bipolar explosions. You can see here how well collimated is this. And this is because neutrino emission is concentrated around the poles. And to see that, these are two snapshots of the evolution, and the variable represented is the amount of energy released by neutrinos as a function of time and per unit mass. And since this is in log scale, you can easily figure out that, and I have forgotten to say that these pink lines over here are identify the different neutrino spheres in the model, and the dashed yellow lines are isosurfaces of constant density. So because of a geometric effect, the proto-neutron star is very flat over here. One focuses very much the energy release in those polar areas by factors that can be 100 times larger than at the equator. And this happens throughout the evolution. Finally, we have early magnetorotational explosions, as this model in panel C, right, or here, which is the same in 3D. And these models can launch relativistic jets much earlier than neutrinos can do any job in the system. And within these jets, velocities as high as 1/3 of the speed of light can be attained. And also the explosion energies are still ongoing, are still growing. We don't have a final value for this number, unfortunately, yet, are reaching many few times 10 to the 51 Earths, approaching the hypernova regime. Jetted explosions are a solid result in 3D magnetorotational supernova community, as has been shown by a number of groups, some of which are represented in the audience. The other set of models that we have considered are those which undergo chemical homogeneous evolution, and then they have different masses. In the upper panels, here we have in 2D models which explode as ordinary neutrino-driven supernova explosions, but of those are two types. One's like model A08 or A20. Sorry?
Question, if you don't mind, your question.
Yes.
Yeah, so I see that, the speed of the outflows has reached speed of light over 3, but I'm wondering, just knowing that gamma ray bursts, for instance, can have Lorentz factors of up to 1,000, is that just a computational limitation that can't develop more powerful, more relativistic jets, or is that just
no? Actually, this is just a very preliminary and incipient phase. The central engine for a GRB has still not been formed. You will see later. I mean, in these models, the central engine, if it's a collapsar, will take tens or the order of tens of seconds to form. And we are running here only for a few, 2, 3, or 4 seconds, and some models up to 10 seconds. But still, the accretion disk has not formed around the central black hole. And if the central engine is a proto-magnetar, we are still too early on. The supernova shock is within the star. And we expect that after the supernova shock runs out of the surface of the star, then the conditions might be such that the density decreases sufficiently, and the proto-magnetar may drive ultra-relativistic outflow. Or the black hole, by Blandfors-Najek mechanisms or whichever other mechanisms, can drive an ultra-relativistic jet. But this is later, not at this stage.
Okay, so now we
Okay. Good. So as I said, there are two different outcomes for the central compact remnant in these neutrino-driven explosions. Either they form black holes, or they form neutron stars, which are living there for a little while, at least, if not forever. This is the case of model A05 or A17. Then we know these models are especially interesting because look at, for instance, the diagnostic explosion energy. If I guide your eye through this set of lines, look at this dashed black line. This corresponds to model A05. And what you see is that the explosion energy starts to develop after 1.5 seconds or so, which is the time where explosion takes place. And then suddenly it just blows up after about 3 seconds. This is because a proto-magnetar has been formed there, and a strong wind is just pushing from behind this ejecta and increasing dramatically its explosion energy, which is really skyrocketing. In addition, we have models, which are just represented in this bottom set of panels, which develop early magnetorotational explosions. Those are much more collimated. And there are transition models like A39, where it's not clear whether they are magnetorotationally driven or neutrino driven. This is a mixture of effects. We have already run 3D models but only up to about half a second or so of some of these models, which are more interesting, magnetorotational explosions and one of mixed type, and they are starting to build up the same picture as before in the previous models, but they are confirming the results of our 2D models. One problem, if you want to call it this way, of the models in this common envelope, in this chemically homogeneous evolution, is that they produce insufficient nickel mass. We have estimated the amount of mass that these models may trigger in 2D, and this is smaller than 0.05 solar masses. To produce a hypernova or a superluminous supernova, if the luminosity is triggered or is driven by nickel decay, you need of the order of at least 0.1 solar masses of nickel, or typically for a hypernova of the order of 0.3 or more. However, this is not a problem if the luminosity of a superluminous supernova is driven by the interaction with the circumstellar medium, or taking into account that these protoneutron stars might be stable for many seconds, but eventually may collapse to form a black hole, and later on a collapsar. And once you form a collapsar, winds emerging from the accretion disk may be excellent sites to produce nickel, as was figured out already by McFadden et al. In 2001. Here, let me guide you through this busy slide. First, let's look at what happens in this upper left plot, which is the mass evolution as a function of time. And please note that the maximum time here is 9 seconds. So you can clearly see a separation of lines, a separation of models. Some models do never cross, and during this evolutionary time, the maximum mass allowed by the equation of state. So these models have protoneutron stars that so far are not susceptible to collapse to a black hole. And they may persist for very long times as protoneutron stars, if not forever. A very important feature is that after about 0.4 seconds after bounce, one develops a local maximum mass for all these models. And what do these all models have in common? They are all having a colloidal magnetic field slightly larger than that obtained from stellar evolution calculations. The model coming directly mapping the stellar evolution rotational profile and magnetic field is the red line, and it produces a black hole. A tiny change in the topology of the magnetic field yields a protoneutron star, and probably a neutron star. And I stress the need of running sufficiently long because the evolution is highly non-monotonic. Note that after the maximum, the mass of the PNS is decreasing. And why is that? This is because the magnetic field is so intense in the outer layers of the PNS that it's scratching this part and brings the outer layers of the PNS into the bipolar flows. So accretion is not enough to balance the mass loss, and the mass of the PNS decreases. But this is not monotonic. In some models, the one with the strongest magnetic field and dipolar morphology, the effect is dramatic. And you end up with a neutron star after about 2.5 seconds, which has only 1.6 solar masses. In other cases, the situation is unclear. That's why we have called these models proto-magnetar candidates. Some of them may collapse to a black hole, but on time scales of tens of seconds. But in the meantime, they are proto-magnetars, and they may fuel high energy transients. In contrast, these models may have encountered black hole collapse during the computed time, or they clearly will produce a black hole if we would continue our models. The separation between these models, which we call proto-collapsars and proto-magnetar candidates, is also clear in the rotational energy contained by the compact remnant, below 6 × 10⁵ ergs for proto-magnetar candidates and above that value for proto-collapsars. Now, since in the case of chemically homogeneous evolution models, we have considered progenitors of different masses, we may probe the different criteria available to predict the compact remnant and explosion type from the properties of the stellar progenitor. Among them, we have the Ertel et al. 2016 2-parameter classification obtained for non-rotating, non-magnetized stars, which may only produce neutrino-driven supernova explosions or no explosions at all. The classification of Ertel et al. Consists of two parameters. The M4, which is the mass when the entropy per baryon equals 4. And I remind you that the entropy per baryon in a massive star grows from the center towards the outside. And eventually you just look at when it crosses an entropy per baryon of 4. And the mass derivative right at this point, at the point where the entropy per baryon equals 4. Now, if you represent the value of mu4, the mass derivative, as a function of the product mu4 times m4, Ertel et al. Found that models below a critical division line, which is in black here, and also for our models here, produce supernova explosion and leave as residual, as remnants, neutron stars. While above this division line, black holes are expected and explosions are very unlikely. Well, the classification does not work very well for our models, because here the red triangles represent models which produce proto-neutron stars. And you can see that they wander around the division line. So there are proto-neutron stars where black holes should be. And vice versa. We have models like K20, which produce a black hole under the conditions in which the stellar progenitor should have led to a neutron star. So this classification criterion, which is very valid for, sorry? Okay. Is there a question?
Okay. What time do you think?
Is there a question?
11:02? Oh, like right now? You're with us?
Okay. I'm hearing.
Thanks, Greg.
Sorry, I'm hearing a lot of conversations. Okay, good. So the thing is that this two parameter classification does not really work well for rotating and magnetized models. Instead, a more accurate classification is just obtained if you just look at the compactness parameter at 2.5 solar masses. And according to this classification, we have that black holes form if the compactness parameter is below 0.2, and proto-neutron star form if it's smaller than that, right? And this is valid at least for chemically homogeneous evolution models. I must do a disclaimer here, and is that all PNSs that we are computing are relatively massive, with masses above 2.2 solar masses, but below the critical mass set by the equation of state. But as the evolution goes on, the ratio of rotational energy to gravitational binding energy approaches a few percent. And then if we would run these models in 3D, or as we are doing, some of these models may collapse because of non-axial symmetric instabilities to form black holes. An important point is that a number of properties in the remnants are ordered according to the strength of the poloidal magnetic field, especially the mass of the compact remnant. Larger values of the poloidal magnetic field of the same stellar progenitor model yield to systematically smaller masses of the PNS. This is in 3D. In 3D, the evolution has not been taken for so long, and therefore some models seem that, well, it's clear that as in 2D, this model has reached a maximum mass and this won't collapse to a black hole. But some other models nearly have a flat evolution or a very small slope, positive slope. This might be, this is because accretion is shut off much more over the PNS once the explosion is ongoing in 3D. But it might also be a question of numerical resolution. We have to investigate that in more detail. Another thing that happens when you increase the poloidal magnetic field is that the explosion energy in solid lines here grows, right? So this is ordered according to the initial poloidal magnetic field in the stellar progenitor. The same happens for the maximum radius or the speed of propagation of the supernova shock. Larger poloidal magnetic field, larger velocity of propagation of the supernova shock. Other properties display a much more complex interplay with the rotational profile and are difficult to classify. In that paper with Matteo Bugli and others in 2020, we have studied the influence of the angular coherence length of the poloidal magnetic field. And for that, we have considered the collapse and post-bounce evolution of the very same model, 35 OC, 35 solar masses in main sequence, but assuming different distributions of poloidal magnetic field. These distributions correspond to multipolar fields with progressively larger multiples, from a dipolar magnetic field here in the upper left to an octupolar magnetic field here on the bottom right. Now, the formation of a proto-neutron star that does not collapse to a black hole is more likely the lower the multipolar order. So for a dipolar field, it's more easy to keep stable a proto-neutron star than for a multipolar magnetic field. And on the other hand, another thing that happens is that the smaller is the multipole order, the largest is the explosion energy. Here you have the case of a dipole magnetic field. This is a hydrodynamic case without magnetic field. And in the middle, you have L equals 2, 3, and 4. So why is this relevant? Because the angular size, so the angular coherence length of these fields is smaller the higher the multiples. And then you are coupling smaller regions of the PNS to the outer medium. And this is very important if you want to preserve the structure of the PNS from collapse. Let me go through a small subtlety expanding on this point of the coherence length. Let's examine in a bit more detail how we map from 1D to 2D or 3D. First of all, when the magnetic field in stellar evolution has a lot of power in a small scale because it results from the growth of the Tyler-Sprout instability. So this is just the spectrum of the poloidal magnetic field of one of our models. Since the evolution is not from a consistent MHD evolution, this magnetic field does not respect the solenoidal constraint. And we, when mapped to 2D and 3D, we need to reconstruct a field which preserves the solenoidal constraint, and this mapping procedure is not unique. Indeed, we face another problem, is that the stellar evolution grids in 1D are finer than the grids that we can afford in 2D or 3D. So we need to interpolate. But when you interpolate, you are smoothing part of the finest scale of the magnetic field. And you are also losing magnetic energy. Effectively, when you interpolate, you are increasing the coherence length of the magnetic field. Now, in the figure, we observe the collapse phase, not post-collapse, of various models derived from the 35 OC model. We have considered here different ways of producing the mapping from 1D to 2D. Note that the energy stored in the poloidal magnetic field component, displayed here for the reference stellar evolution with this dashed black line, does not change much during the collapse following our standard procedure of mapping. This happens because most of the small scale structure is dissipated during the collapse, and at the same time, compression acts against that and rises the energy in the poloidal field. Overall, there is a balance, and you end up basically at the same level of energy which you started from. In model ROS, the red lines here, what we do is to smoothen the poloidal magnetic field before interpolating. Then, obviously, in this smoothing, we are decreasing the poloidal magnetic field energy. But since there is less dissipation during collapse, it ends up at the time of collapse with the same poloidal magnetic energy. Now, in this other model, we renormalize this smoothing so that we start from the same energy content as in the original stellar evolution model. And what do we get? What we get is an evolution where the final energy stored in the magnetic field is 20 times larger than that in the reference model. What are the consequences of this variegated pre-bounce evolution on the long-term post-collapse phase? Well, here you have the evolution of the mass of the compact remnant. For the reference model, it's this black line, which goes and forms a black hole. And then these two models form proto-neutron stars. When you simply smoothen the colloidal magnetic field and do not renormalize here, this trajectory here, in the post-bounce phase, you follow basically the same path as the original model, and this will form a black hole. But when you smoothen and renormalize to get the same energy level, you see that this model wanders between producing a black hole or producing a PNS. It is unclear. And you see that this is a small technical detail which may change the fate of the progenitor. That's what I claim, that the small variations in the parameters of stellar evolution may yield to very different fates in the post-collapse evolution. Let me briefly comment.
Sorry, you have 1 or 2 minutes more.
Right, yeah, I'm finishing. Let me quickly comment on the nucleosynthetic yields of our models that have been computed only for a subset of 2D cases, which confirm that magnetorotational supernovae are additional sources of our process nuclei in addition to mergers of neutron stars. And I don't have the time to go here into the details, but I want just to comment on the fact that the amount of nickel formed by our 2D models is still small to explain the hypernova branch in most cases, and the energies that we have in our explosions are still small compared to this hypernova branch. But the good news is that when you do things in 3D, and those are the solid lines here for the explosion energy and the mass, the ejected mass in the bottom panel, you get more mass ejected and you get larger explosion energies. So all these plots here would go or are going in the right direction, and I will be glad to tell you about these models once they are finished. So let me sum up and conclude saying that in spite of their high compactness, our cores develop neutrino-driven or MHD-driven supernovae. The feedback of the explosion dynamics on the compact remnant is such that the PNS mass grows by accretion along the equatorial region, and it may decrease its mass by ejection along the polar directions. In some cases, the PNS may collapse to a black hole within time scales which can be of the order of 2 seconds or more, depending on the model. A fraction of these models will form collapsars. Other models without a black hole contain rapidly rotating, very flattened, and strongly magnetized proto-neutron stars, which may yield to massive proto-magnetars. There is a strong dependence of the magnetic field topology, coherence length, and to a lesser extent, on dimensionality in our results. 3D models confirm the explosion type found in 2D. We still need to use larger resolutions and longer evolutionary times. And one characteristic of these models is that accretion is strongly suppressed, and therefore no black holes have been formed so far in the 3D models. Detailed nucleosynthesis calculations of 2D models confirm magnetorotational supernovae as additional sources of our process nuclei. And regarding the consequences for stellar evolution, we have to say that cores with a specific angular momentum distribution is smaller than that obtained from a standard 1D stellar evolution calculation form black holes and eventually collapsars. While cores which have a distribution as it comes from a stellar evolution and moderate to large mass loss rate may form proto-magnetars. The results are extremely sensitive to a quantity which is very much not controlled in stellar evolution calculations, the colloidal magnetic field. And we need a better treatment, definitely, of the torques in convective layers to have a more realistic magnetic distribution. And that's it. I apologize for the overtime. Thank you.